Hi everyone, my name is Bilqist Zahra and I'm going to explain about my result of fluid mechanics experiment. So what am I going to discuss is first there is preparation, assembly, experiment, analysis and the last is conclusion. Okay, the first is the preparation. Considering the budget and the pandemic situation, the experiment needs to be cheap, easy in shipping, easy to examine, and available in online store. But here, the used components are preferable. Therefore, we picked water flow from reservoir using Bernoulli's principle that the total budget is less than 100K with no shipping costs. Okay, the next is the assembly. The assembly of the experiment is really easy. First, we have to make a small hole at the bottom of the bottle. And next, we need to attach the straw into the hole. Then, make sure there will be no leak or blockage for the water flow. And the last is to put marks for two different water levels. So here you could see the final assembly in the figure 1. The experiment. This is a water flow from a reservoir with one outlet. The experiment aims to determine the outlet velocity from the straw. Therefore, Bernoulli equation is used. The tasks need to be done is first measuring the heights of the water levels, and then calculate and compare the output flow of the two different water levels. Here, indicator that is used is the distance of the water when it comes out of the bottle. Here you could see in the figure 2 the schematics of the experiments. So the schematics is used to help the calculation later. For the analysis, we need to define the Bernoulli's equation first, using one inlet and one outlet. Here, the inlet and the outlet pressure are the same, which is the atmospheric pressure, so we can cancel out the pressure. Since I set the datum at the outlet, then the HE will become 0. And because it is a reservoir, meaning there is no water input, the inlet velocity will become 0 as well. Therefore, the equation for outlet velocity will become square root of 2 times g times the height of the inlet. This is the analysis 4.8, the higher one, and the data from the experiment shows that the H straw is 1.8 cm and the HA is 23 cm. So the H1 is 21.2 cm. Using the previous equation, the outlet velocity of point A is 2.04 meter per second. And for the point B, the lower one, the water level is 10 cm, meaning that the H2 will become 8 cm from subtracting from the H2. And using the same equation, the outlet velocity of point B is 1.27 meter per second. From the result of calculation, it is known that Vb is smaller than Va. We could see in the figure 5 as well that the distance of the flow in point A is longer than point B. For the last conclusion, all the components did work properly and was a success experiment. In one inlet and one outlet reservoir case, using Bernoulli's principle, it is known that higher water level produce greater output velocity, and greater output velocity meaning that the water will flow out of the bottle further. I think that's all for fluid mechanics experiment, and we're about to move to the next presentation. Okay, hi again. So this time I'm going to present about my heat transfer and thermodynamics experiment result. So the same as the previous presentation. So I will be discussing about the preparation, assembly, experiment, analysis, and conclusion. First, preparation. It is still the same with the previous, that the experiment needs to be cheap, small, so it will be easy in shipping, and available in online store. However, this time, it will be better if the experiment could be done in a short period of time. Therefore, the group come up with thermoelectric experiment, so that it can use both of thermodynamics and heat transfer principles, which are second law of thermodynamics and Seebeck effect. So for the assembly, it's quite easy but still challenging. First, we need to stick all thermoelectrics between the composites. Make sure that you put thermoelectrics in the center. Next, make a frame from the block and put the composites on top of the frame. And then, connect all the cables of the thermoelectrics together, also with the lamp. Last is to prepare a thermometer and hot as well as cold fluid. In this case, I used candle and ice. And here, in figure 1, we could see the assembly of thermoelectric experiment. So this experiment aims to change heat transfer of a system into electricity. Using second law of thermodynamics, it is known that total entropy of a system will never decrease. Therefore, in the analysis, efficiency of a system is calculated. It indicates that entropy is increasing, so that not all heat transfer can be transferred into work. And for the heat transfer analysis, I used heat equations to calculate the heat rate of the system. Well, it is known also in Seebeck effect that net heat rate between the fluids is equal to the power produced to generate electricity. Okay, tasks that need to be done is first calculate and analyze the effect of net heat rate when the temperature difference is higher or lower to the power produced. The indicator that is used is the intensity of the lamp. And second, is to calculate the efficiency and then relate it to the second law of thermodynamics that not all heat transfer can be transferred into work. And here, the indicator that is used is the melting ice. And here, we could see the schematic of the experiment, of the thermoelectric experiment in figure 2. And in this figure 3, you could see the equivalent thermal circuit of the experiment. So here, the state 1 is for the hot body, and the state 2 is for the cold body. Okay, for the heat transfer analysis, so this equation is from the Seebeck effect, that the power is equal to net heat rate of the system. And from the equivalent thermal circuit, the previous one, I picked the Q convection 1 as the Q1 and the Q convection 2 as the Q2. Here, Q convection is equal to convective coefficient times the area and times the temperature difference. And the parameters are, first, there is the length of the four thermoelectrics, which is 16 centimeter, and there is the composite temperatures, which are 27 degrees Celsius or 300 Kelvin. And then there is temperature of the cold fluid, which is 77 degrees Celsius or 280 Kelvin. And we have the temperature of the hot fluid, which is 35 degrees Celsius or 308 Kelvin. And the last is the convective coefficient. Here I assume that the hot fluid has bigger convective coefficient, which is 60, and for the cold fluid a big 22. And this is the calculation using the previous parameters. So the Q2 is equal to 11.26 watt, and the Q1 is equal to 12.29 watt. Therefore, the power produced is 1.03 watt. So, when the temperature difference between the fluid is 28 degrees Celsius, it took 5 seconds to turn on the LED lamp. You can see in the figure 4a that the LED shine brightly. However, when the ice was taken off the composites, meaning that the temperature difference between the fluids was smaller, the LED is getting dimmer. So for this, you can see the figure 4b for comparison. So from the previous, it is known that the power A is greater than the power B due to the higher temperature difference between the fluid. And LED lamp in case A also shines brighter than the case B. Well, the intensity of a lamp doesn't depend on the power produced. Here, power is equal to voltage times current. As the power goes higher, the voltage is also getting higher since they are proportional. That is why the LED is getting brighter. It is because of the voltage, not because of the power produced. And for the thermodynamics analysis, using efficiency formula, when the work out is divided by the heat in, the efficiency of the system is 8.34%. Since it is not 100% efficiency, it indicates that not all heat transfer can be transferred into work, and it also indicates that there is an increasing entropy in cold body. So it makes the heat transfers from hot to cold fluid. This is why the ice is melting in time. The conclusion from the experiment, Seebeck effect shows that the net heat rate of a system is equal to the power, since bigger temperature difference between the fluids produces higher power, and power is also proportional to voltage. Therefore, higher temperature can make LED turns on brighter. And from the second law of thermodynamics, it is known that not all heat transfer can transform into work, and that is why efficiency will never be 100%, meaning that entropy is always increasing in the cold body especially. And it also means that the heat transfer is from hot to cold temperature. Feedback for this course. I really liked the course, very flexible and free. However, I think it would be better if the experiments were already decided, so all the students would have the same opportunity to finish the experiments. So there will be no excuse for lateness, and I think it will make you easier to check the final work in the end. Okay, so that's all from me. Thank you.